So today, I'm going to talk about, probably I'm going to talk about like administrative stuff first. I'm going to talk about the exam, sort of like exam stuff, exam 2 info, and then we're going to talk about 13.2, which is vector calculus on vectors. Of course, if there's any homework questions, I'd be happy to answer those as well. So let me, if there are questions about the homework, let me get through talking about the exam first, and then once we talk about the exam, we can move on to homework questions, and then I'll start talking about sort of different derivatives and integrals of vector functions, which is pretty straightforward, but then also the interpretation of them. So as far as exam 2 goes, I have a list here of things that I like. So I don't know if you guys have noticed, but this class is sort of a grab bag of ideas that are all over the place. There's not really any help for that. It's just kind of the way these classes get, because we need to teach you stuff that you use in your engineering classes, and science classes, and computing classes, and business classes, and math classes, and I guess just have to do it all. So the ideas covered on this exam are going to include, just to remind you, parametric equations. That was 10.1. Parametric calculus. That's 10.2, and that covered things including derivative, second derivative, area, and arc length. We talked about polar functions. That's 10.3. We talked about polar calculus. And 4, and that covered derivative, area, arc length. Remember that a big part of the polar function which is in here is plotting. Then there were the lame sections. So 3D coordinates. Not lame, probably just mostly review for people, right? So the 3D coordinates, that was 12.1. Vectors in R3, that was 12.2. And the big idea is when you study vectors in R3, just the notion of length and magnitude, kind of where that's introduced. Dot products, 12.3, which includes angle, orthogonality, scalar and vector projections, cross product, which is 12.4. Here we had determinants, the idea of vectors being parallel using the cross product, the area interpretation, and then, so here's the debate I'm having with myself, which is, we have one more section here, which was 12.5, which was about vector planes and lines. we'll talk about my internal debate. The vector planes and lines was 12.5. That covered the idea of the parametric and vector and symmetric equations for lines. And then for lines, planes, we talked about normal vectors, leaving planes from limited information, creating planes from points, and then the vector, scalar, linear equations. And then we talked about the distance from a point to a plane. Now, having written this on my notes earlier, and having written this on the board now, my feeling is that this is more than sufficient knowledge to put on this test without trying to push it and put chapter 13 on here too. Right? So my feeling right now, unless there's like strong objections to this, is that while I have introduced chapter 13, my inclination is to cut the content off at the end of 12 and just do 10 and 12 on this test. Now, if people really want chapter 13, I'm happy to write chapter 13 questions too, but like more limited scope seems like it's a beneficial thing to do. So is there anybody who really wants me to put chapter 13 on here too? Okay, so if we're not going to do chapter 13 on the exam, then what I'll do is I'll take all of the chapter 13 homework and I'll make the actual set due date next week. Okay. And I want you guys to focus. I'm going to keep going on chapter 13 in the short term, but I want to also, for the next couple of days, I really want to privilege questions people have about this stuff. Okay. If there's anybody in here who ignored some of this homework or got lost and didn't pick it up and you want to reopen, make sure you write me an email if you're past the auto extension date so I can reopen it for you. Like, I don't care. I'm working around what's built into WebAssign. So if stuff looks closed, it's not. It's just I can't make WebAssign open things permanently if you're behind. As far as preparing for this stuff, you should prepare for these things by looking at the quizzes that I gave you. So I did not give you a quiz on 12.5, but you've had quizzes that cover all the rest of it. Everything I'm going to pull for an exam is going to come basically from the homework. And I'm going to give you another one of these sort of big sheets of lots of practice problems like last time. Remember that if I give you a review sheet with topics in it, it will have questions for those topics sorted by topic inside, right? So it's not going to look like a practice test. It's going to be a big review that has questions located next to their topics inside of it. Okay. So I'll give that out on Tuesday and we'll talk about that on Thursday. Are there questions? I mean, you already taken the exam, so you kind of know how they go. Are there questions about anything about this that I can answer? Yep.
About how many questions?
It's going to be around the same length as the last one. So it's, I think last exam was 6 questions, but a couple had a couple of parts. So normally the way you should think about this is if I have 50 minutes to give you an exam, the amount of time per question is going to vary somewhere between 5 and 10 minutes per question. That's what I allocate. So somewhere between, 6 and 10 questions, but normally I try to get around to 8. Because I can't possibly ask about everything in here, but I can ask about individual questions about a lot of different things. So where people go wrong on this one is there just a lot of different things to keep in mind, right? A lot of different setups. We've got 3 different setups. We have sort of this vector setup, we have a polar setup, we have a parametric setup. That's what's hard to keep distinguished. Anything else? Yeah, so I think last time the average amount of time that people took on the test was about 42 minutes is what it turned out to be. I'm probably going to write it. That's about where I try to write my exams. So about that, about 40 minutes. And no shame if you go over. Yep.
Is it going to be like Is the way chapter 10 and 12 based or is it more of one and one?
Well, I mean, it's gonna, you should think about not equally, I mean, the material is, I mean, what, there were 4 sections of chapter 10 and 5 sections of chapter 12 or something like that. So it's probably gonna be about the same. Because I'm gonna do a little bit from each, I mean, I'm gonna cover all. I'm gonna cover something from parametric land. I'm gonna cover stuff from polar land. And I'm gonna cover stuff from the sort of like 3D stuff that we started doing, like vector stuff with dot products and cross products and line planes. Like there's really, you shouldn't think of 2 areas, you should think of 3 areas. A polar area, a parametric area, and a vector area that I'm probably gonna have to give about equal time to all 3 pieces. This is part of the reason why I'm cutting the content off, is so I can like keep a handle on how much is going on in this exam. Because I don't want you to be guessing what I'm going to put on here. I think it should be pretty obvious what I'm going to put on, right? The ideas are pretty clear. We had parametric equations and we drew them, we did calculus. We had polar equations and we drew them and did calculus. And then we did a bunch of vector computations. Anything else? Okay, so I'm going to give you a version of this written up with questions on it that I'm going to post tomorrow after class. Okay. So get up on your homework. If you need your homework reopened, please send me an email so I can open it back up for you again. Really concentrate on this. Don't worry about getting behind on chapter 13 because I'm going to push all that homework off to next week. Okay. And the first section of chapter 13 is pretty easy. Okay. All right. Anything else before I go on to math? Yep. I am going to have extra office hours this week. So it's been a nightmare trying to find times where people can come into my office hours, but I'm going to try to do another, it's like I did for the last one where I have big extended office hours on multiple days. So my plan right now is to have office hours on Tuesday and Thursday, Tuesday, Wednesday, Thursday, and then possibly Friday morning as well. That's hard because I have meetings on Friday morning, but for sure longer office hours on Tuesday, Wednesday, and Thursday. And I'll make an announcement about that. And if you can't make any of the hours I post, let me know so I can post, I can schedule something else. Anything else? All right. Okay, are there any questions I can answer about anything in the homework? Yeah.
So there's one problem they did, I think, I forget what chapter it's from, there was 2 points, and they said find an equation for all points equal distance from those 2 points. And I think what they did was they got like a midpoint and they created a plane from that. I understand how they got that midpoint, but I don't understand how they created the equation.
Okay, that's an excellent question. That's a really beautiful question. Like I will say that's the sort of challenging question that's like almost appropriate for an exam question, right? Because it's like, it's not so hard to do once you know how to do it. Okay, so that question specifically says, if you have 2 points, we can just, I'm just going to draw 2 points down randomly because the technique works on all of them, right? So I'm going to give myself some nice integer values for this. And then if I really wanted to be cute, I would make sure that I could divide by 2 and get a midpoint that didn't have any fractions in it. So there's 2 points. And these are points in R3. This is the important thing here is these points are in R3, right? And so the answer to this question, if I have 2 points, and I say every point that's equidistant from both points, it's going to be, I mean, there's a midpoint, but then you can imagine that like there's an entire plane of solutions to the problem. It's not a line that is, the picture you might have in mind here is, oh, well, there's 2 points and it's everything that looks like this because these distances are the same, right? Top and bottom. But in 3 dimensions, there's a whole plane of points that satisfies this. 2 points like define a 3-dimensional set of equidistant points, not a 2-dimensional set. So the idea is sitting in here in the middle, there's some plane. Like if I want, I can draw it like this. What information do I need to write the equation of a plane? What's the minimum information I need to write an equation of a plane? I guess I'll say in words what we're doing here. We're finding an equation for the set of points equidistant from 3, 4, 3, and -1. So the first thing is just to know this is a plane that's going to solve the problem. But if I'm going to write down an equation of a plane, what do I need to have? I'll give you a hint. That's the variable in this equation. So I need two pieces of information to write down the equation of the plane. If you don't like this form, you can think of it like this. In either case, I have two pieces of information I need. I must have the normal vector to the plane, which is the ABC, and I must have a point that's on the plane, which is the R naught. That's the X naught, Y naught, and Z naught. If I want to write the equation of the plane down, I must have the normal vector and any point that's on the plane. So you pointed out that there's a point that we know is on the plane, which is the midpoint, right? The midpoint of these 2 points is equidistant from each of them. And so I know that if I just connected these 2 things with a line and I found the midpoint M must be inside this plane. It has to be. It's equidistant from this and this. Now I'm hoping that you guys are still, in some sense, carrying around the midpoint formula in your head. Like the midpoint between, and if you're not, at least you can sort of eyeball what the midpoint is. Like what number is exactly between -1 and 2. So you go to your handy dandy number line and you go, let's say -1, 0, 1, 2, 3. Okay, so 1, 2, oh, it must be 1. Because 1 is like 2 jumps this way and 2 jumps that way. So at least you could figure it out, even if you didn't have the formula. Right? Okay, so 1 is exactly between 3 and -1, or if you like, a more sophisticated way to do it is the midpoint is equal to the sum of the 2 numbers, or the distance, right, the difference of the 2 numbers divided by 2. Right? X1 minus X0 divided by 2. That's actually not the midpoint formula. What am I doing? No. The sum. You add the 2. So I was calculating the distance, not the midpoint. The midpoint is X0 plus X1 divided by 2, comma Y1 plus Y2. Why am I changing indices here? Y0 Y1 divided by 2, comma Z0 plus Z1 divided by 2. It's the average of the numbers, right? The midpoint is the average of the numbers. I apologize for writing down the distance between the numbers. So if you do that, I don't carry this around in my head. I just think, well, it's halfway between. It was the average of those numbers. 1, 2, 2. I carefully set the problem up so that the averages would all be integers. Right. There's a point that's in the plane. How the hell am I going to find a vector that is perpendicular to that plane? Where am I possibly going to get that? Does perhaps it already exist in the picture? What if I just connected the midpoint to one of these points? That vector right there, when I take the midpoint and I connect it to one of these points, must be orthogonal to everything in this plane because that's the shortest distance, right? And so the n, the normal vector here, you could use the vector that points between these guys. Right? So the midpoint doesn't just get you a point that's in the plane, it helps you define what the normal vector is. So the normal vector here would be 1 to 3 is 2, 2 to 4 is 2, 2 to 3 is 1. The vector that connects M to this point 3, 4, 3 is this. You could go the other way and it would be totally fine. Right? All you need is a vector orthogonal to the plane. It could be any length, it could be in any direction. So if you connected M down here, that would work. Hell, you could find the vector between these 2 points and it would work. Right? In any one of those cases, the vector will be okay. Right? There's at least 4 normal vectors that you could put down here that would work. The easiest one is, for me conceptually is just to think, well, I got this midpoint, I might as well use it. So what that means is, you know that the point M, 1, 2, 2 is in the plane. And you know the vector N, which is 2, 2, 1, is perpendicular to the plane. My number line over here. And so that means that the plane must have the equation. I mean, that's the easiest way to write it. The way most people like it is not to use the vector formulation. So A times x minus x naught plus B times y minus y naught plus C. And C minus C naught is equal to 0. Well, ABC comes from the normal vector. And then the x naught, y naught, and z naught come to the point. 1, 2. All of this is just computational though, right? I mean, the point is that the most important thing about this problem is being able to visualize this picture. And then if the problem didn't point out that a plane is the sort of thing that is a set of equidistant points, you actually need to know that. All right? Yep. You can do that too, but I'm trying to emphasize the vector geometry in the class. I mean, if you know that that's what's happening, right? That you've got this sort of like the distance formula going in the background. That's like the analytic geometry approach is to do it that way. Because there, what you're emphasizing is the calculus viewpoint. Right? That you're somehow, that's actually how you find the distance, the shortest distance between a point and a plane is to take a formula like that and then optimize it. Right? So you are absolutely correct. That's a correct answer to the question for sure. But I'm like the hardest thing about moving into vector analysis is to think in terms of vectors, which is why. So I'm not discounting what you're saying. I'm trying to emphasize the vector like viewpoint. Anything else? Thanks for pointing that out. All right, let's do some calculus on vectors. I have uploaded prior to the class here the 13.1 video, which I apologize for. Can I erase this? Is it still writing? Okay. All right. So we're almost to some of the most beautiful results in calculus, but first we have to go through how to do calculus on vector functions. So this is the content of 13.2. Is derivatives and integrals of vector functions. So the reason we can even do this, if you imagine that you've got a vector function R of t is equal to f of t, e of t, h of t. The reason we can even come up with a notion of derivatives is that if you remember from last time, as long as R is continuous, I can just push a limit inside of it, right? So recall that the limit as x goes to x, or t goes to a, of R of t is equal to, well, the component-wise limit as t goes to a, f of t, limit as t goes to a, t, limit as t goes to a, h of t. So limits go inside vector functions. Well, that's going to mathematically justify as a definition of a derivative. So we can define the R dt is equal to the limit which goes to 0. So R t plus h minus R t. That should look really familiar, right? That's the definition of the derivative. Now, if that does not look familiar to you, I'm going to point out that far from being some sort of like, mystical formula they teach you at the very beginning of Calculus 1 and you can forget for the rest of your life, that the idea that derivatives come from difference quotients is one of the most fundamental geometric viewpoints in all of mathematics. Okay? Difference quotient, like the reason that we learn this is because there's physical meaning behind things. Okay? This is a meaningful quantity. You should at least be carrying around the idea in your head that when somebody writes a derivative on the board, it's not shocking that this is how it's defined. If somebody said, "I'll calculate a derivative for a vector function," you would hope that this was the definition. The reason it's the definition is because it's like the definition of the old scalar derivative, but in each component. Let's see if we can come up with an interpretation of it. So I've got some curve, RT. There's some particle traveling along that curve. And at some point, you decide, from that point right there, I'm going to figure out what the derivative is. So what you're really doing here, if you imagine down here is the point 0, 0. Remember that a vector function has these arrows that connect it. That point right there, you can think of as being RT. If you advance time a little bit, so time moves along by h units, then you're going to get a different vector. So this vector right here is R of t plus h. You're further along the curve, right? It's moving along. The particle has slid further down. So here's R of t, and here's R of t plus h. What do you get when you subtract those? I have two vectors, and I subtract them. I heard a voice. Is it you?
Yeah.
All right, now you're on the hook. Now, what do you get? Here's A. Here's B. I'm going to draw you this parallelogram. That's also B, and that's also A. I'm going to put the diagonals in here. One of those vectors is A plus B. One of the diagonals I drew here is A plus B, and one of them is B minus A, right? B plus A and B minus A. Which one is A plus B? A long one or a short one? It's a long one, right? This guy right here that connects all the way across the top, that's A plus B. It turns out that the other diagonal is A minus B or B minus A, depending on the way it points. Okay, so B minus A goes this direction. So this vector right here, that's B minus A. So subtractions of vectors go across the short diagonal of the parallelogram. So when you're looking at a picture like this, and I say take this vector and subtract that one from it, this is the result. That vector right there is R of t plus h minus R of t. That's useful. This is actually why we're using this vector formulation. What is going to happen to this vector as I slide that point closer and closer to this point? Let's say I take this point, this h, and I let h go to 0, which means this point right here gets closer and closer and closer up here. So for example, another vector that you might get out with something like this. That one right there, this little vector is like an even closer version of that one. What's the result going to be? What does it look like is going to happen? You're going to get a tangent vector out the other side. I mean, these are like secants. And now I'm asking you guys to remember way back in the ancient past here. But ultimately, what will happen is these vectors are going to end up pointing in the same direction as the tangent to this line. The vectors, in some sense, are measuring like what direction a particle is moving at this point right here. So the vector that you get out of the limit is the tangent vector to the curve. But it's more than that. It's more than that. Because if you have a point R of t, you compute t of t. Then actually not t. R prime. You actually have two pieces of information contained in R prime. They're not actually telling you this yet because they don't think you're sophisticated enough to get physics before math. So this is actually, if R of t represents position, what is the derivative of position? Velocity. But now I get an actual vector for velocity. An actual vector. I mean, they've told you, oh, velocity is a vector quantity. But look, it's actually literally a vector now. And it contains two pieces. I mean, the whole point of all of this is that when you get out of the derivative at a particular point, you calculate the derivative of the point. This vector contains both the direction of motion and its magnitude is the speed. So the magnitude of this vector is going to measure how quickly the particle that makes this path is traveling. This is an incredibly important vector, it turns out. Okay. Now, they don't do this until 13.3, but I think it's important to see what the motivation is here. The reason why we want these tangent vectors is because they both tell us what direction the curve is tangent to, but also the magnitude of the vector that comes out also contains information. Okay. All right, so as they define this, they say this. I'm going to write something down on the board, and I want somebody to tell me why they do it. So they define this special quantity. Capital T of t is equal to R prime of t divided by the magnitude of R prime of t. So what is that? So I've taken this vector, but now I've divided it by its length. So what information is left over when I do that? If I take a vector and I divide the length away, so I've got a unit vector, what information is left? Better than that. So that's part of it for sure. What else? Because remember, this was still a vector, right? I've taken a vector and divided by a number. This is still a vector. So there's more than just plus or minus here. Direction, right? Unit vectors tell us direction and nothing else. A unit vector is a vector of length 1. All I care with the unit vector is what direction it points. So what I'm doing is I'm saying, okay, well, there's a vector here. I wish I had some chalk with multiple colors. There's a shorter vector here, capital T of t, which just tells us what direction the curve is turning. As the curve goes, this thing right here is like the slope of the tangent line in some sense. Doesn't tell us anything about speed, it just tells us how the curve turns. So there's a t, there's a t, there's a t, and there's a t. They're all unit vectors, they're all the same length. And so in some sense, what the t is telling us is how the curve is turning as things move in space. T of t basically is the slope vectors for the tangent lines. Called the unit tangent vector. And it gives the slope vectors tangent lines. And that acts exactly the way we want a derivative to act, right? That's the derivative is supposed to tell us slopes. It is telling us slope. The reason that we do this normalization here is because this could be very big or very small, right? And if we're just trying to measure slope, we don't actually care about how fast things are moving. We just care about the direction of the tangent. Okay. So what that means is, in the scalar land, we had y minus y naught is equal to f prime of x naught times x minus x naught. That's the point slope form of a tangent line. This works for a function in scalar functions where y is equal to f of x. So we get a very similar equation when we're doing these guys. Looks like this. So the tangent line, I guess we'll call it, let me make sure that I'm not, do they just call this LT? Do they call it anything? Derivative of vector functions, unit tangent vector. They even have you compute a tangent line? Okay, that's weird. But if you think about what you need to do in order to put a tangent line at a given point, if that point right there happens at t is equal to t naught, then the direction vector is going to be equal to t of t naught. That's the slope there. And the point is going to be given by r of t naught, because that tells you where on the curve you actually are. Remember, this curve is given by r of t. So that point right there, you can think about being at r of t naught. So if I know the direction vector and I know the point on the curve, then I could say L of t is equal to the point that you know on the vector plus the direction vector times the parameter t. And that should remind you a lot of this. Basically the same equation, but with vectors. This is the general equation for a tangent line to a vector function. Point, slope. Like that. I mean, you don't need to memorize the formula. You just need to remember that what's going on in the background here is this. All right, so let's compute an example. Any questions about this? Again, I'm trying to emphasize the vector picture here and not the specific computations, which is why I'm giving you guys these sort of generic equations, right? I'm not trying to make you learn at a super abstract level. I'm trying to emphasize that the power of the vector setup is that you can just do this. Which means that if you knew t and you knew r, you could just write down all of the tangent lines in one go. Okay, so let's actually do one. An example here. R of t is equal to 1 plus t cubed I plus t e to the minus tj. The sine of 2tk. And don't get caught up in these component notations. If you'd like, you can immediately think of this as in vector form. There's R. The reason that people do this, they break these things out of these component vectors, is because sometimes it's really convenient to be able to work this way in applications. Okay, so how does R prime of t work? Well, it works exactly the way we think it should. If I want the derivative of a vector, I just take the derivative of the components. R prime of t is equal to d by dt of 1 plus t cubed, d by dt of t e to the minus t, d by dt of the sine of 2t. Notice that this requires that you remember how to compute derivatives, unfortunately. So, you know, annoying things like the product rule are continue to be active. So in this case, you're going to get 3t squared plus e minus t minus t e to the component. Each component gets its own piece of the derivative. Because the derivative is a vector. The derivative of this is 3t squared. The second component takes the derivative of this, which gets you that guy. The third component is the derivative of sine of 2t, which is 2 cosine of 2t. Remember that the derivative of a vector function is a vector. Okay, this is a really easy mistake to make. Derivative vector function. Vector. Don't accidentally mix them all up together. The second part of this question might say, find t of t, just the unit tangent vector. Now these could be ugly because I have to compute the length of that. So you got the trust that if I ask you to do this in a sophisticated setting, that if I ask you to compute the length of this vector, that it's okay for you just to write down some mess of algebra without doing it. T of t equal to r prime of t divided by the length of r prime of t. So I had better be able to normalize out the length of that vector. The length of r prime of t equal to, oh God, I've got to take the square root of these big nasty things. Component 1 squared plus component 2 squared plus component 3 squared. Then you don't simplify anything, don't work anything out. In a problem like this, you just leave it. That's okay. It's the length of r prime right there. So if you wanted to compute t, you would write down 1 over this big mess, times the vector r prime of t, which was 3t squared e to the minus t minus t e to the minus t. This guy right here, this is, I'm saying that this is the correct version. But the idea here would be that no matter what t you plug in, the length of this vector is always canceled by this quantity that you've computed here. So, why do I say crap? Because unless this is very simple, you would never compute this by hand. It's important that you understand conceptually what's going on here. Is that you're deleting out the speed and just keeping the directions. Okay. Okay. All right. Okay, so perhaps unsurprisingly, if you can compute derivatives, there's nothing stopping you from computing anti-derivatives, right? What? Oh, come on, it's calculus. You gotta have both. So the integral of a vector function is just defined to be the integral of the components. I mean, that's easy, right? If I wrote down something like, as an example here, I wrote down, I'd like you to compute the integral of the function t squared sine t dt, right? There's a vector function right there, and I ask you to compute its antiderivative. It's the function that would have this as its derivative. So you just integrate piece by piece, the integral of t dt, the integral of t squared dt, the integral of the sine of t dt. It's 3 integrals for the price of 1. Look at all this practice you're going to get. T squared over 2, comma, t to the third over 3, comma, integral of sine is minus the cosine of t. Now you might ask, where's the plus c's go? But there was a plus c here in the x coordinate, and a plus c here in the y coordinate, and a plus c here in the z coordinate. So really, there was just an arbitrary vector that got stuck on there. So literally, integration works exactly the way you think it should. I'll point out, well, the same exact logic here also applies to the fundamental theorem of calculus. Actually, so I want to know, this is a good question. What is the fundamental theorem of calculus?
The integral between 2 points of a function is the one minus the other. I don't know what the describe it.
Oh, wow, you're going to go all the way. Okay, so let G. Okay.
From A to B.
Okay, so the integral of f dt from a to b is equal to f of b minus f of a, where f prime is equal to f. That's the fundamental theorem of calculus, part 2. Did we actually remember part 1? It does come from the x minus h. Yeah, basically, you can differentiate the integral. So, but this is the part we care about right now. That was just a trivia check. This formula also works for vector functions, like the same exact way that you think it should, because it acts on each individual entry. So if you can compute the antiderivative, you can plug an a and a b into it. So if you have an r prime of t and you integrate it from a to b, what you get out is r of b minus r of a. You integrate it to get the antiderivative, and then you just plug the endpoint in. Okay. So calculus just works. That's why Newton and Leibniz invented it, because it just works. Right? So there's not really conceptually more here until we go on to the next section, which is about arc length and curvature, because that's when we start picking up features that are specific to vectors. The idea that I want you to have in your head when you're practicing 13.2 is calculus works the way that you think it should, because we can just apply it to each entry individually. And we're going to need a little bit more subtlety to figure out like how we can use this to study curves moving through space. All right, so yes, get studying. And this homework I think is already posted, or if it's not, it will be shortly. But this will all be due next week. Concentrate on the exam. Yes, right. But then you're gonna go. Like, see, that makes sense. You go left side, it'll be like sine of 3 cosine. Dude, whatever. You still have to remember how to integrate. And then it's gonna put it from like 5 or 3. I tried to keep the really ridiculous questions off of the website assignments. Like I tried.
Are we gonna get any equations on the test?
The only one I might consider giving you is the derivative formula, whatever it was, the parametric second derivative. They isn't messed up with the doctor. They just schedule it for another day. And they just tell me, they do that. Yeah. I've had that done to me. It's not a big deal. Thanks for letting me know. Yeah. And then I am pretty behind on the board. How long do I have to do it? Like I mean, I'll extend it to the end of the quarter. I just want to do it. Yeah. Okay. Yeah. Send me an email and tell me which ones you want extended, and I'll do that. Thank you. Hey, how do you find out when courses